Hey, what's up, chem peeps? What in the heck are we gonna do in this vid? More Lewis structure fun. We're gonna continue talking about shapes of molecules and how they're accounted for by hybridization theory. This vid, however, short and sweet. We're gonna just look at defining two terms. What is a sigma bond? What is a pi bond? And then, once we've defined them, you want to be able to determine the number of sigma and pi bonds in a molecule. Alright, so let's define a sigma bond. A sigma bond is a covalent bond that's formed by orbitals overlapping end to end. The electron density is concentrated between the nuclei of the two atoms involved in the bond. Here's a great image that represents a sigma bond. Half-filled p orbital from one atom, half-filled p orbital from another atom. When they overlap end to end, you get what's called a sigma bond. Next, let's define pi bond. Pi bond is a covalent bond formed by orbitals overlapping not end to end, but side by side. Here, the electron density is concentrated above and below the nuclei of the two atoms involved in a bond. Great image to represent a pi bond. You have half-filled p orbital from one atom, half-filled p orbital from another. Instead of directly overlapping end to end, they overlap side by side. The electron density is above and below the nuclei of the atoms. All right, now you have to know what type of bonding is involved in single, double, and triple covalent bonds. Recognize that if you have a single bond, that is a sigma bond. Double bond is composed of one sigma bond and one pi bond. And then finally, a triple bond, one sigma bond, two pi bonds. All right, we're going to take a look at three molecules to help us understand how we can identify sigma and pi bonds within the molecule. We're going to start with some ethane C2h6. As you focus on this molecule, the first thing I want you to do is think about it in Lewis structure format and recognize that each of the carbons are sp3 hybridized, because each carbon has 4 regions of electron density surrounding it. The sp3 hybridization gives us the tetrahedral shapes that we would see about each carbon atom. All right, as we think about the bond that would form between the two carbon atoms of ethane, it's going to be a single bond. Therefore, it's a sigma bond that forms between the two carbon atoms. When we add the hydrogens, again, we're forming single bonds. So each hydrogen-carbon single bond represents another sigma bond. So in our molecule of ethane, we have a total of 7 sigma bonds because we have 7 single bonds. All right, let's take a look now at ethylene C2h4. Again, start with the Lewis structure and recognize that now we've got a carbon-carbon double bond. Here, we're going to have sp2 hybridization about each carbon atom because each carbon atom has 3 regions of electron density. sp2 hybridized. That sp2 hybridization is what gives us the trigonoplanar geometries that we see about each carbon atom. Now remember, in ethylene, we have a double bond. One of those bonds is a sigma bonds, where the orbitals directly overlap, end to end. Adding the hydrogens, notice once again, will form additional single bonds, additional sigma bonds. But what's different in our molecule of ethylene is that remember that the carbon atoms are double bonded, and the sigma bond only accounts for one of those bonds. The unhybridized p orbital about each carbon atom create the pi bond where they overlap side by side. Notice that the electron density is above and below the 2 carbon nuclei, our pi bond. And then finally, let's take a look at acetylene. Again, start with the Lewis structure where we see the 2 atoms of carbon triple bonded together. There are 2 regions of electron density about each carbon atom, making the hybridization sp hybridization for both carbon 1 and carbon 2. The sp hybridization is what gives us the linear shape that we see about each carbon atom. When that sp hybrid orbital overlaps with the sp hybrid orbital of the neighboring carbon, we create our sigma bond, directly overlapping. If we add in the hydrogens, again, single bonds, therefore additional sigma bonds. But recall that the carbons each have 2 unhybridized p orbitals. And when the unhybridized p orbitals overlap, they're going to overlap side by side, not end to end, giving us 2 pi bonds in the triple bond overall. All right, so I want to come back to these three examples just to quickly identify the number of sigma bonds and the number of pi bonds involved in each of them. For BF3, we have 3 single bonds, which means that we have 3 sigma bonds. The orbitals in each of these bonds are overlapping end to end. We don't have any double or triple bonds, so we don't have any pi bonds. Boom. But take a look at carbon dioxide. We have 2 double bonds. Recall that a double bond consists of 1 sigma bond, so we have a total of 2 sigma bonds and 1 pi bond each. So we have a total of 2 pi bonds. And then finally, C2H2. In this molecule, the hydrogen-carbon bonds are single bonds, each indicating a sigma bond. Then we have a triple bond. One of those bonds is going to be end-to-end overlap, or a sigma bond. So 3 sigma bonds total. But within that triple bond, we also have 2 pi bonds, overlapping side by side. Boom. So, big things here to recognize. Single bond, sigma bond. Double bond, 1 sigma, 1 pi. Triple bond, 1 sigma, 2 pi. And if you can do that, you're good to go. Have a fantastic day.